first. All right. So what we are going to do is just the continuation from last time. All right. So we have a couple more exercises for you to try applying the calculus in the electric field calculation problems and see how it goes. All right. So I understand that some of you don't like this much. However, I have already selected only parts of the problems that I think that is sort of like not too complicated, but it showcases the utilities having the calculus in our hands and what can we apply those calculus, integral calculus to calculate electric field, okay? And for the problems that have like super complicated settings, then we're not going to try to do that because I think the complications is in the mathematics, not in physics. So it's just enough for you to see maybe here what I'm just already selected here, just two more exercises here that we can go through together, and then you'll have a chance to see what does it mean by vector calculus that I sort of like talked about last time. All right. So just a brief, sort of like a flashback a little bit here. If you remember what we did last time, we're just trying to calculate the electric field from a charge that's continuously distributed in a rod of length L and is oriented along the x-axis. All right. So you kind of like, I think, remember that. Yeah.
Okay.
So what we are going to do now is, I mean, contrast to what we did last time. Last time, we didn't see much of the vector aspect of this because all of those tiny, tiny mini electric fields that generated from that tiny, tiny DQ, yeah, right, remember that? They are all pointing along the negative x direction. So when you want to add all those DE, that mini electric fields, you just do the algebraic sum. You just sum numbers because they are pointing along the same direction. So you just take all those magnitude of the DE and sum them up. So that's why what you saw last time was just everything just come down to just a regular algebraic integral. So there's nothing new there. So now here, we need something else to showcase that you are integrating or you adding vector quantities. All right, guys, try this. All right. Woo. All right, guys. So what we are doing over here is now we have a ring of charge, okay? And the ring has a radius A, and you have a uniformly distributed positive total charge Q on it. Calculate the electric field due to the ring at a point P, okay? Lying a distance X from its center along the central axis perpendicular to the plane of the ring as shown in the figure. Okay, you guys, you want to try this out first? That sounds good? Maybe not. All right, so just follow the whole procedure that we did last time, guys. So don't be afraid. All right. You just, attack this kind of problem head on, and then it's going to be fine. Okay. So first, you have to sort of like analyze just a tiny piece of charge at a time. So what you do is just cut a slice of charge. Yeah. It's just like a tiny piece of that. And of course, every slice will contain a tiny amount of charge. So we're going to name it DQ just like before. So let me highlight in red there. Cool. All right, so forget about the rest of the charge, just only this DQ, how much electric field you will get at point P. Just imagine that. So that's easy, Bojan, that's no big deal. So because now you know the distance from DQ to the point P, you can label it using like R, the distance R, which R can be calculated using, from the geometry over here. It's just a Pythagorean theorem. So it's going to be A squared plus X squared over here. So those are the two. So you say R is just the square root A squared plus X squared. So it's no big deal. Everyone can deal with the R easily. Okay. So let's say that the DQ eventually will generate electric field at point P to be just a tiny piece of E as well. Cool. All right. Oh, sorry, guys. Give me a second here. All right, you guys keep. Okay. So how much is the electric field due to that tiny charge DQ, guys? So which is done from Coulomb's law or from the equation that you use to calculate electric field is just going to be dE, that tiny piece of electric field that you got from that dq is going to be K, the charge generating the field, dq, divided by r squared. That's it. You're done, guys.
Okay.
So this one is no big deal. All right. So everyone knows how to set this one up. Okay. Now the complications that you're gonna have to face here is this. You're gonna have to keep slicing that dq one more time, right? Let's let's give it another slice. So you have another dq here, and you're gonna have to just keep doing it. Another dq there, another dq there. Actually, you have to do continuously around the ring. You guys with me? You just slice it like DQ, 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 until you complete the whole piece of this charge on the rings. All right, now let's imagine this. Each DQ will generate another DE. All right, so that means for each one of these DQ, you will get another DE coming out here. All right, and then another DQ, you get another DE there. Another DQ, you get another DE there. You guys with me? All right. So now you have to imagine along with me. If you slice those DQ, and each DQ will give you one DE, but then you're rotating those DQ around the ring. Can you imagine what the DE will trace a surface or like a shape of something, right? You guys sort of like imagine that. So if you imagine that each DQ will generate one of the DE vector on the right, and if you keep rotating around the ring, you're going to have the DE generated in the form of what? It's going to look like a cone. You guys with me? Does that make sense? You get a cone of DE. I don't know. I'm drawing this sort of like makes sense to you guys. Okay, you're going to get a lot of DE, DE, DE that's sort of like on the surface of the side surface of the cone. Cool? And that's what you want to do the summation on. This. You want to sum all those vectors that is pointing on the side surface of this cone. Cool? All right. But then you look at this one now. This is the vector summation now. So if I really want to put this whole thing in an equation that contains the vector quantity, I have to say something like this. It's a dE vector. And it's sort of like it's pointing our hats back, right? That's what you did before. But then what you have to do is just you have to do the integration here. So you want to do the summation of all the dE here. And at the end, you're going to get the total electric field at point P. This one is fine. But in reality, this is just like an equation just telling you what you want to do. But when you really want to do the real thing, right? You're not going to writing like this. You have to have somehow a way that you can actually do the summation. So usually when you have to sum vector in like various directions, what did you do? You do the components, right? You break a vector into two components, maybe along the x-axis, the other one is along the y-axis, or you can say one along the horizontal axis, the other one is on the perpendicular axis, right? We're gonna do the same thing here, guys. Focusing on this. So if you look at one particular DE, like the first one that we just drew, okay? And now if you do the component thing, so that means I can break this into into a perpendicular direction and a horizontal direction. So I can throw away the original. Now you see, okay, so then this is good. So that means if you keep doing this breaking into two components, on all of those vectors on the side surface of the cone, what will you get, guys? Well, then that's kind of okay, because if you look at the, let's take a look at the opposite one. So you do the same thing. You break it into the vertical, you're going to have a horizontal here, right? And if you keep doing this on all those vectors, the vertical component will contain all of the vector that is perpendicular to the x-axis in all directions. You guys with me? That perpendicular direction will pretty much fill up the whole circle there. So that means what you can get out of this one is you're going to get a complete cancellation of this. You cool with this? Okay, so that means that perpendicular components all cancel. They all just get canceled away. So you won't have any that perpendicular directions of the electric field left at all. The only thing left for you to add is just all those components that just going along the horizontal axis. So once again, this total, even though it looks like a vector calculus, you have to sum the vector quantities, but from the symmetry of the problem, this one gets reduced down to the problem of just like the previous problems. You only need to add the x components of the dE. You guys with me now? You only need the dE along the x direction. That's all you care about, because the dE along the perpendicular direction already got canceled out from our analysis here. So what is that dE along the x? Well, Ajahn, that was just dE that you saw before. That was the original dE. But then you only need just the x components. Well, Ajahn, we know the angle. That's a theta. If this is theta, this is going to be theta. It looks dirty right now, but I think you guys got my geometry down here. So you just only need the cosine theta components of the dE. Cool?
Okay.
And this is the one that you need to do the summation. So you do the integral of the dE along the x-axis. And the good thing about this one is now you come back to the algebraic sum one more time. But having to do the components analysis, that's part of the vector calculus that I'm talking about. But it's sort of like a simple way. You sort of like get away by, cancel one portion of the vector out, and then you only have to sum just the other components. So you reduce your problems down to just the algebraic integral one more time. All right, but it just gives you one more complications that you have to think of your quantity in vector sort of like fashion first. All right, once you complete this, you will get the net electric field along the x-axis at point P. Cool? All right, so let's continue, guys. So what I'm getting right now is going to be integral of the k dq over r squared cosine theta. That's what you have to integrate. And you're going to integrate every piece of the dq around this ring. So you still have problem, Dan, how am I going to do that integral? But at least I'm going to say is around the ring. Let me just put like rings on there. All right, I have to do all of the dq on the ring. All right, it sounds bad, it looks bad, but it's not. Carefully pull out constants for me, guys. What are the constants that I can pull out from the integral so we can just deal with the rest? K is constant. What else? Look carefully, Ajahn. That's kind of nice. The R itself is constant.
Okay.
Right? Because no matter where you are, the distance from the dq to point P is still R anyway. Wherever you are, they are all R. So R is also can be pulled out from the integral. What else? Yeah, the theta.
Okay.
Very good. The theta itself is also constant because no matter where you are on the ring, yeah, the angle that you make with the x-axis is also theta. So I can pull cosine theta out as well. Isn't that cool? There's nothing else for you to do except just the integral of the dq. And what is this? What is the sum of the dq, guys? They already told you that the total charge on this ring is capital Q. That's it. All you need to just take all the dq around this ring. So this gives you back that capital Q. And that's it, guys. You're done. So the answer is going to be K capital Q. Now you can turn cosine theta into adjacent over hypotenuse if you want. And then you say it's going to be x over square root a squared plus x squared. And then x squared, r squared, you already found out is just going to be that square root square. So you can divide it by a squared plus x squared. On and on. Now it's just the way that you just manipulate the final form of this one, but I think you are done.
Okay.
Is that bad? It's easier than you think, I guess. Right? But the complications is sort of like shows up at the point where you need to sum the vectors, electric field vectors. But we just threw in, components analysis a little bit. We just say, okay, Ajahn, all right, the perpendicular components got canceled. So all we need to sum is just the x component of it. And once we only care about one single component, the integral will be just an algebraic summation. You don't have to worry about directions anymore. Cool. Done.
Okay.
Cool. Okay. Quiet is good. I like it. All right. All right. So if this is good, now is your turn. All right. We're going to combine your experience that you got from this problem, just a straight, rod. This problem, a ring, you deal with a little bit of stuff, curved. Now, find me this. All right, guys. The third one. The figure shows a plastic rod having a uniformly distributed charge, capital Q, even though it's negative. So let me emphasize it's a negative charge there. It's a negative. All right. The rod has been bent in a 120-degree circular arc of radius r. So everything just has shown in the figure. In terms of capital Q and the R, what is the electric field due to the rod at point P, guys? Want to give it a shot first? Yeah. Woo. All right, guys. Just give it a shot, like, head start for a couple minutes. What will be the first line of equation, or what kind of like first setting that you need to get things started here? What should I do to deal with this? What do you think? All right, the first thing first, you have to do just exactly what we did before. You slice a tiny piece of charge, and that tiny piece will contain amount of charge dq in there. Okay, that's too big. Sorry. My bad. All right, here we go. There. That's dq in there. And now you might say, about John, this sort of like come in a curve. So it's not like on an x-axis or anything. So just keep that in mind. We had that before back in here. Every time you slide this one, it actually comes in like a curve piece. But because last time we got away with the total charge is just Q, so we didn't have to do anything with it. But here, we don't know, right? We'll see. But at least that a first note that you just have to take note in your head that, okay, even though it has a dq in it, but your slice will contain a distance. Let me call it ds for now, right? Because it's not on the x-axis, so let's use like some s, some distance or whatever. Okay, next, what else? Well, Ajahn, it's just like before, this dq will generate an electric field everywhere. And because we are looking at just particular point P, what happened there? So that's your radial direction. And because the negative Q is negative, it will generate electric field pointing towards it. Cool. Nice. And that, you can name this to be a tiny dE. Okay, that's no big deal. I think you see what the setup is. Now I can write down the magnitude of that dE, right? Even though this is a dE vector, right? But the magnitude of that dE is just going to be the K constant. The Q to generate the field, it's just going to be dQ. Okay. And divided by the distance square. And now because this is the radius of an arc with the radius R, and the point P is already located at the center of curvature. So the distance is going to be R squared. That is just the distance right here. R. Cool. All right. So I can just leave that one out. Okay. So that is the magnitude of the electric field at point P due to that tiny piece of charge dQ. So what do we have to do? Well, Ajahn, what I need is you just keep slicing dQ. So dQ on the top there will generate an electric field pointing towards it. That's another dE for it. And you just keep doing the slide. You do it slide. Oh, sorry, that's an error. You just keep doing the slide, dQ, all the way down to the bottom. Okay, and at the bottom, of course, you also have the dE coming to it, like that. You guys with me? So that means if you think smoothly from the top ends of the rod to the bottom ends of this rod, all those dQ will generate dE, 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 dE. Yes? Does that make sense? So each DQ that you slice from the rod will generate DE. But then once you move that DQ around the rod, there will be DE along with it, DE, DE, DE. So all those DE that you're generating will eventually build up a shape of like a part of a circle. Think of it that way. That filled with the DE. Like there's a vector DE full. I mean, this part of the circle will be filled with the DE painting around it, having point P as the starting point for those vectors. Cool. All right. So far, so good. All right. Now, this is what you want to take the summation on. I want the sum of these vectors. That will be your net electric field at point P due to this plastic rod. So far, so good. How can we do that? Any suggestion? It's just like the previous one though, right? But just think about it, John. It's symmetric again in the sense that, okay, here we go. I'm going to trace back a little bit here. You look at this one. Now you know that you're going to have to sum all those DE everywhere. But if you just look at one of them at a time, look at the DE, guys. In red, if you break this into two components, you're going to have a vertical and horizontal component, just like before. So look at the green. The green, I think this is the obvious one. If I break the green down, I'm going to have this. I'm going to have that, right? I just get rid of the original. That's my green component of that. And look at the opposite of this. Let me look at the blue. Let me do the dark blue here. So the blue, I can do the breaking as well. So the blue will break into horizontal and vertical. Cool. Do you notice something here? You will always have its buddy, its pair, that is pointing in the opposite direction when you look at the vertical direction. This part will cancel with this. And because this configuration that you're looking at is symmetric above and below the x-axis, with me? So that means you will get equal amount of the vector component that is pointing up and the vector that's pointing down. So what I'm saying over here is the vertical components of all these DEs that you generated from the plastic rod eventually will cancel themselves out altogether. Nothing left in the vertical components. Cool. So once again, all you care about to add is just that X component of the DE that you need to add. Wherever you are on this one, you only care about what is going on along the x-axis again, because the y components eventually got canceled. Completely symmetric, equal amount on up and bottom, I mean up and down components. So that means what I care about is just we only want to add or to sum the electric field DE that is pointing along the X components. Okay, all right, but that's not done yet. Let's take a look at this, John. I can write that one out. It's just that original DE. And then now you just want to break this into two in a component, right? So you might want to call this like, okay, I'm going to call this theta, John. So it's going to be DE cosine theta. But this one is unlike the previous problem. The previous problem, the theta is fixed. No matter where your DQ are, your theta stays the same. So that's why your cosine theta can be pulled out from the integral, doesn't give you any headache. But here, this is not the case. It turns out your theta is now varies. So you can imagine that now your theta is now a variable. Depends on where your DQ is. You guys with me? So for example, if you look at the top portion over here, your theta will be all the way out. That is your 60 degree. But if you look at the blue is down here. You have to come down here. I don't know what you're going to call this one. We'll call it later, but that you can call it another 60 degree downward here. And of course, other value of theta will varies from 60 in the upper portion down to the 60 in the bottom portion there. Cool. So now keep in mind that now your theta is a variable. But anyway, all in all, what you need is just, I'm going to have to sum this all together. I want to sum them all. I want to sum the X components of the DE. If you can complete this summation, that is going to be total electric field at point P, and you are done.
Okay.
Okay. So at least now you know how to have your integral set up here. So far, so good. Next, how are you going to do it? We already figured out the DE. Just plug it in. Okay. So why not? Just give it a shot. K dq over r squared cosine theta. This is the one that you want to integrate. And you want to integrate when the theta is from where to where, guys? Now, this is the crazy part. It's not super crazy, but it's annoying. Let's say, let me call it, it's annoying. Do you want to integrate from which angle to which angle? Well, then I say, okay, I want to go from the top to bottom. Some will say, well, I just want to go from bottom to the top. Who knows, right? You have two ways. You want to slice from the top down, or but I mean, eventually, you're going to have to come down into some convention. And if you remember, look at the XY components, yeah, and look at the XY axis. When I write XY like this, do you know where the Z axis is supposed to be? Right? It's an XYZ, right? Cartesian coordinates, right? If X is pointing to your right, Y is pointing up, where is your Z axis? It's a right-hand rule, right hand. We always use right-hand coordinate system. So if X is point to your right, positive X is to your right, positive Y is up. You take your forefinger going from X, curl your forefinger to Y, your thumb will point toward your face. So that means this is actually your Z axis is pointing up. Let me put a dot here. You remember this notation? Maybe if yes or no, I don't care at this point, but we might have a chance to deal with that later. But the point is now your Z axis is pointing to your face. Okay, why do I have to say this? It's kind of like, what's the point? The second thing, if I want to remind you, is this. When you did the math, when I have like a right triangle, for example, and you're going to call this theta, right? Remember something or notice something that whenever you want to refer to the angle, you always measure that angle, or the value of that angle is the angle with respect to x-axis. I don't know, you sort of like noticed that before. So that means the reason that you want to name this angle, and then if you want to sort of like measure the angle, you measure it in this direction. I put the arrow there. You measure counterclockwise, 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 counterclockwise. So if you use your right hand and you curl your forefinger counterclockwise, which direction is your thumb? Your thumb is pointing to your face again, because that is your Z axis is also pointing out. See, that's my whole point. The point is we are always using right-handed coordinate system. So this is the reason why your angle theta is always measured sort of like in comparison, or you start your zero angle from the x-axis, and then you count, or you sort of like look at the angle counterclockwise. And every time that you want to go opposite sense, you want to go down. If you have like another angle down here, you call it alpha, that angle that is measuring downward or clockwise direction, they will give you a negative angle. This is negative. I don't know. Does that make sense, or is it correspond to what you have already studied before? This is what it is. Okay. So why I'm saying this? Because down here, look at the blue. When you say it's 60 degree, actually your starting point of this one is negative 60 degree, because it's below the x-axis. And when you look at the green, when you look at up here, this here, the position over there, that is positive 60 degree. So I hope by saying all this like long and lengthy discussion about the coordinate system and whatever counterclockwise, clockwise direction, and the z-axis, you will understand why do I have to set my limits of integration from negative 60 to positive 60 degree. Okay, let me do the color coded here as well. Got that one? All right. That's it. That's my whole point. The point is, if you want your final results to look clean in the sense that you have like, you don't have any negative sign at the end or whatever, some weird stuff coming out, you have to start from the lower value to the higher value all the time, right? Just like when you do the integral, you always do like the from left to right. If you want to find area under the curve, for example, you start from the lower value of x to a higher value of x. You want to sweep from left to right. You want to go from small to larger values. Same thing over here in angle. If you want to speak about the angle, you have to start from a lower angle value to a higher angle value. So that's why I have to answer the question is which direction that you want to integrate. I have to sum the effect from the dq at the bottom first, right here. And then I do the integration upward, clockwise direction. And then I'm going to end my integral up here. Cool. All right. I need to do counterclockwise because that's where your positive direction is always, it's always been like that. พอรู้เรื่องไหมเนี่ยอาจารย์โอเคไหม is that useful? I don't know. But by saying something like this, I think it might take some confusion or something that's sort of like nagging you for a long time out from sometimes when you solve problems in math or whatever, sometimes you might hit something like this, like why, or like how come my result is like negative, even though when you look at the answer, everything is correct, but why my calculation have a negative sign on it? Maybe it's just because of limits of integration which just get swapped. That's all. You go in the opposite direction. That's why you get an opposite sign in your answer. Okay. All right. Move on to our calculation. Yeah. Just keep going. So once you understand how to set up your lower limits and upper limits, you want to go from smaller value to a bigger value. Now, what you have to do next is just continue on. Just like before. What are the constants that you can put? Oh, whoa. What happened here? What are the constants that can be put out, guys? Okay, K's out. Okay, what else? Well, the R, the radius is still constant here, right? Because it's just it's like a rod and it's being bent in a circular arc. So that means R squared can be also put out. Cosine theta cannot because theta is a variable for you. So theta is keep changing. You have to keep it inside your integral. dq is still there. So now this is not an easy integral anymore. The reason I say not easy anymore because see, we have the same problem again. Your integrating variable is q, but your function that you try to integrate is under theta variables. So you need one more time. You want to have to bridge between the q and the theta. Just like what you bridged before, you're bridging between the dq and the dx back in the day that you do the straight rod along the x-axis, right? There is a way that you can do this bridging by going through the density the density lambda, right? We take the charge per unit length to be something that you can make a comparison. Yeah, so you say, okay, the whole rod have the charge per unit length equal to lambda. So now, even though you slice a tiny piece of it, that ratio stays the same. So we're going to use the same techniques here one more time, guys. How can you turn dq into theta, or how can you turn theta into q? From the logic that you did before, you're probably not going to try to turn theta into a q, right? Because that would be kind of tough, right? Cosine of something q in it is like, that's not going to be easy. So it seems like a very logical way is I try to turn this into something of the theta. Can you do that? That's the thing. Okay, so just like what we had before, we turned dq into something of dx. So we want to do the same thing here. We want to turn dq into something of the theta. How can we do that? Now the figure looks really ugly now. So what I'm going to do is this. Let me open up a new page here. And all right, I hope I go slowly enough for you guys so I won't left anyone behind here. So here we go. So let's take a look at an arc. So I'm just going to draw a nice, beautiful arc for you guys here. Okay, so let me do this. Huge arc here. That radius. Now I have an arc. That's your arc length here. All right. Now I just said, okay, done. I already did slicing. Within this slice contain tiny piece of charge. And we said that tiny piece, it's still take a little bit of space that we just call it ds before. That's fine. Okay. So how can we link between the theta to the dq, even though we don't have that yet? So what I'm going to do next is this, guy. Follow me here. So that tiny ds there will still be covering a tiny angle at the center here with me. So if you name the subtending angle of the whole arc to be theta, you can name this tiny angle to be d theta. Does that make sense to you now? Okay, so that means actually when you look at that super small segment of a circle in orange there, that will give you the connection between the s, the theta, and the radius of the whole thing, just like what you had before back in the day of an arc length. Okay, remember this. If you blow up this whole, not blow up, but if this whole Q over here has an arc length of A and the same radius, right, R, so you already got the concepts or the definition of the theta, the angle is going to be arc over R, right? You have done this before. But then we just do the same thing, but it's just way smaller. So what I can do is when you look at the tiny stuff there, that you just have like a mini portion of your circle, the theta is going to be the same thing. It's going to be the arc length is ds divided by r. See, same thing. No difference. Just everything just way smaller at this point. So what I can get from the last equation over here is I can say that tiny arc length ds is just r d theta. Cool.
Okay.
Okay. And now you can link back between dq and ds. We already did this before. So you already said if you want to get the amount of charge within the length of whatever, you can multiply by the charge density. You guys with me? Just like what we had before with the dq equal to lambda dx. And lambda is just charge per length. Yeah. So when you have the charge density per length, all you need to get back to the charge, you just multiply by the length. Yeah.
Okay.
So same thing over here. If you know the lambda charge per length, you want to get the charge in there, you just multiply by the distance that the charge is being covered, right? It's in there. ds. Lambda ds is just the dq. But then now you know more because now your ds right here can be written in terms of the theta. So it's going to be lambda r d theta. And that's it. That's what you want. That's how I can convert and sort of like interchange the variable q with the variable theta. That's what it is. So plug that back in here. Now I'm getting towards the end of the calculation now. K over R, integral of the cosine theta. Now I can turn that dq into lambda r d theta. See, I just plug this thing back in here. And I still have some more constant that I can pull out. Oh, this is R squared, sorry guys. So whatever constant I can still pull out. So what I can pull out further is just the lambda can be pulled out. 1r actually get canceled. So I can just say 1r left in the front. And all you have to do is just the integration of the cosine theta d theta from negative 60 to positive 60. Can you do that now?
Okay.
Yes, you can, because the integral of cosine is just sine theta. So what you have is going to be k lambda over r sine theta from negative 60 to positive 60. Cool. And everyone knows sine 60 is root 3 over 2. Sine negative 60 is negative sine. So that means you're going to get twice of the sine 60. So you're going to get root 3 out of it. So that's it, guys. I can just mark that this one will give you root 3. And that's it, guys.
Okay.
Done with the answer. So it's a root 3 k lambda over r. That is going to be your net electric field at point P. And which direction is pointing to? It's going to point to your right side. It's just a positive x direction because you don't have any vertical electric field component at all. So your net answer is going to be sigma E at point P. Vector is just sigma EP that you just got. I hat, and you are done. Cool.
Okay.
Not bad. I know it's pretty bad. But I think this is going to give you the hardest kind of problem that is going to show up in this course. All right. I'm not going to go any deeper than this, or I'm not going to have anything that's sort of like too complicated than this one. I think I would call this like your upper limit of difficulty that you're going to face in the integral problems of the electric field. All right. So I'll have some more exercises for you to try in the homework, but I think this wrap up what is going on with the Coulomb's law in electric field calculation in combination with the calculus, which is the continuous charge distribution problems. Any questions? I think you have had enough of calculus for today, I guess. All right, guys. So if this is good, then I think this is a good point to take a break. All right. And when we come back, we'll move on to another concept that is equally important, right? So we're going to move on to electric potential after this. And I think just take break right here, guys. Okay. Session first. Now, what we have next for you is going to be another concept in electric. It's called electric potential. And this word potential, it's, yeah, same kind of potential that you probably have done it in potential energy under gravitational field. So it's the same concept one more time. So as you can see, the concept that you use in the field calculation and the force, they already have a similarity with the gravitational field and force. Now, electric potential will use the same concept of the potential that you did use in gravity, believe it or not. So they are exactly the same stuff. So what we are going to introduce to you today is going to be what is electric potential and what is the difference between that and another one, annoying one, electric potential energy. Right, it sounds funny because these two terms are actually different terms. The upper one define one thing. When you add the word energy into it, you have another one. So these are the two things that we are going to learn, but they are closely related again. All right, it's just a conversion between one to the other. So we're going to learn that today. And eventually we're going to have to take a look at the relationship. Once again, you're going to make everything like come in full circle. So we're going to link back between the charge, the field, the force, the potential, and eventually potential energy that we're going to learn today. Okay, so that's a whole picture. So, all right, guys. So you're going to have to listen to my sort of like lengthy speech again. What is actually potential, guys? Potential energy, because you're familiar with the potential energy from gravity, right? So what is potential energy in reality? When I say in reality, I mean in your real life, that you really have to define it, right? Even though you might have used it before, the mgh, that's your potential energy in gravitational field. So let me mark on that, mgh. So have you ever wondered how did you get that mgh from? Whoa, all right, this is, right, it's like a serious question here, okay? And what kind of thing that you will be able to get out of electric instead of gravitational field? I can just give you the end result right now without proving anything to you. I can just say potential energy in electric. So let me put the subscript E, and then let me put the subscript G here just to distinguish. One is for gravity, the other one is for electric. I can just write the equation by using the comparison that we have been doing all along. Mass is the charge. G is the field, and H is just the displacement. We are done.
Okay.
We got the whole idea now, because we keep saying that in the topics of electric, charge behave just like mass in gravity. The field E behave just like gravitational is acceleration G in gravitational fields, and H is just the height. It's just a, distance from one place to another. You can just call it the distance D. So that's your end sort of results that you can expect from this. You should be able to get back to this formula QED by doing the whole concept of the actual definition of potential energy. And I'm going to show you now. Okay, this is annoying, I know, but stick with me just a little bit. It's going to look confusing. Here, everyone look at this one first. And what do you see? It looks pretty close to what we learned in thermodynamics. Yeah, I mean, thermodynamics is pretty much conservation of energy. So when you want to go from point A to point B, okay, and you do some work. So there is a work done from A to B. All right, now, and if I write it like this, you have the change of the energy, potential energy, that's what you call it, but with a negative sign in it. This one looks familiar because we pull this one directly from the not Coulomb law, sorry. We pull this one directly from the first law of thermodynamics. Yeah. Delta U equal to Q minus W. And because we're not talking about heat anymore in this story over here, so forget about heat. So with the clue that you have back here and what you learned before, so you can assume that this work done must be the work done by the system. Let me put on top over here, right? We learned that before. In thermodynamics, you say, okay, if the system perform works by itself, the result is going to be the energy of the system gonna get reduced. And hence the negative sign. Because if the system perform work, energy will get dropped. But stick with the concept of the change. I have been emphasizing this all along. The change is final minus initial. So it's going to be U final minus U initial all the time. So this equation has nothing to do with electric just yet. This is just a conservation of energy, correct? Now, here we go. Come back to my mass here. Okay, guys. So if I drop this one down, bam. Everyone knows the potential energy up here is going to be higher than the one below. It's mgh. So the top one is a higher edge, higher height, or whatever at the higher elevation. So this one has a higher potential energy, gravitational potential energy. When I let it go, it dropped down to the floor. The bottom of my screen has lower potential energy. Upper portion of my screen has a higher potential energy. When I let it go, potential energy of this mass is reduced. So the change of this potential energy is negative. You guys with me? Here comes the question. Who does the work? Who is doing this pull? Who is doing this pull, the pulling of the mass from the top of the screen down to the bottom? The answer is the gravity itself. And right now, the gravity is our system. You guys with me now? What kind of system is this? I mean, I don't know, you believe it or not, but the system that we are talking about is the earth and my mass. That is our system. Come again, guys. This is mass. Actually, this mass is being pulled by the earth at this point. Once I let it go, the mass and the earth get closer together. So imagine this. You think of it like you have an invisible spring attaching my mass and the earth. Does that make sense? Yeah. So if it's on the floor, if my mass is on the floor and I pull this one up from the floor to the top of my screen, I'm stretching that invisible spring. You guys with me? So imagine with the spring is kind of easier for you to imagine, right? Okay. So think about it. It's like if you have an invisible spring that the earth is connecting with the mass. And when I want to stretch this one up, I have to perform work. I am the one who's stretching this spring out. And when I let it go, the spring just snap back. Bam, the earth and the mass spring just snap back. Does that help? Okay, so all my point I'm saying over here is, of course, if you let your system go, have your system perform works by itself, you're going to get a negative sign all the time, because every time that system perform works by itself, it means it's going to lower their own energy. The energy of the whole system gets reduced. Cool? Okay. And that is the reason why you have to be careful with who's doing the work. Because now, if you want to go against the field, guys, I want to bring this mass up. What do? You or me or whoever, somebody has to come in and grab this one and pull this one up against the field. Gravity is pointing down. You are trying to go against the field. So that means if you perform works by external force, what you do is you go against the fields, mean you increase your potential energy. So what I'm saying over here is the conclusion is gravity is pointing down. Every time that you go against the direction of the field is down, you go up the field, right? You go upstream. Why to Nam, yeah? So when you try to go upstream, that's when you go to a higher potential. Cool? Okay, so there are always two sides of the story. You want to have your system do your work itself, so that's lower your potential energy, of course. Or if you want to go against your field, that's when you do increase the potential energy of the system. And that's how you define your potential energy. That's all. Okay, so one conclusion that you can get over here is you can say right away that when you go along the field, you are going in the direction that you lower your energy. And whenever you go up against the field, that's when you increase your potential energy. That's it. That's my take on this. Okay, just have this in your sort of like your in the back of your mind first. Okay, so that's what I'm trying to get you to understand this. So to define your potential energy now is going to be easy. Okay, so let's take a look at this. Now everyone knows the work done by the field, negative, right? Because we know if the field perform the work by itself, you're going to lower your potential energy. That amount of potential energy change will be the negative of the work done by the system. How much work is being done by the system? Now let's come back here, guys. Almost done, almost done. Stick with me here. So now let's turn our attention to the electric setting. Now you have an electric field pointing down. See, figure on the right. Now you have a charge standing at point A. You let it go. It's moved to point B. How much work is being done by the system, which is the field? The field is pointing down. So you say there will be an electric force equal to the amount of charge multiplied by the field. Everyone okay with this already? Right? Every time you know the fields, multiplied by the charge, you get the force. How much work is being done is just, see, you move from A to B. Your distance D has a direction is downward. So your displacement is pointing down. So you take the F vector, which is just the Q times E vector, and then you do the dot with the D vector, right? Try to do the whole thing. So the work done is just F dot the displacement S. So in this case, it's just going to be Q, E, D. Got that one? Almost there, guys. we got all the terms defined here. It's almost done here. All right. However, what you're seeing over here is this is the work done by the system. So you need to put the negative sign in the front. So I put the system on here. So for you to put it here, you need this. Plug it in here with the negative sign. Okay. Because you know that whatever the work done that you calculated over here, you get a positive number because force and displacement is pointing in the same direction. But you're going along the field. See that? You go along the field. The field is pointing down. You're going along the field. So you're going in the lower potential energy. Hence the sign negative in the front. That's it, guys. That is pretty much almost the definition of the potential energy difference between 2 points. All you need to do is just take the Q times the E times the displacement, and you put the negative sign in the front, you get the potential energy difference. There you go.
Okay.
This is the most annoying part of the lecture because it's like, I sort of like take you guys back to the root of how you define the electric potential energy. Yeah. But the reason I really want to have to talk about this one is because so many of you don't really like sound like kind of annoyed with Ajahn. What is this for? That negative sign. Right? You guys is like, Ajahn, why this formula has a negative sign in the front? There's nothing to it. That's just our agreement. We agree that when you go along the field, you're going in the direction of lower your gravitation. It's not gravitation. You're going in the lower potential energy. So if somehow the physicists back in the day of like maybe 200 years ago, they decided that, hey, up here, this is low potential and down here, this is high, then your life will be pretty much like upside down. I mean, and I mean, your life stays the same, but I mean, the way that we communicate will be upside down because we will say that every object will go from lower potential to a higher potential. That's kind of like it's counterintuitive, right? So we kind of agree already when you are up high, that's also high in potential energy as well. So that's why when you go along the field, see, field is down here. There is the field. If you move along the field, you are moving in the lower energy change direction. Your energy is changing in the decreasing direction. Okay.
Okay.
I think maybe I already talked too much about this whole formula, but my whole point is just for you to be able to see where the negative sign is from. That's it. Okay, cool.
Okay.
Now come back to us here. It's time for you to meet electric potential. Whew. So we already defined electric potential energy, which is just another kind of potential energy because we already had the field. But the electric potential turns out to be a very simple concept, guys. It's just potential energy per unit charge. Does it sound familiar? Per unit charge. So the feeling was just like force. When you do the force per unit charge, you get the feel. And this is the one that your friends was just like talking about. Is that the test charge? Yeah, you can think of it like a test charge. So whenever you take the force per unit charge, you get the magnitude, or I mean, you got the value of the electric field. Same thing over here. If you have U to be your electric potential energy, you do it per unit charge as well. You're gonna get electric potential, guys. That's it.
Okay.
So the concept is simple. You do it per unit charge, you get to the potential. And the unit of this potential is volt. Yeah, you guys familiar with this? The answer, I mean, the question is why then? Why do we have to introduce electric potential? Isn't it already good that we already had electric potential energy? The answer is this. I think the problem is with this. Whenever you have a mass, the mass is easy to track. I mean, you can, identify, hey, this is my mass, M. I control this mass. You can do projectile motion. You can slide this one on the floor, give it to your friends, whatever. This is a piece of mass. It's easy to track down where it goes. But it's not like this in electric. Imagine the electric charge that running around in your computer, laptop, in your notebook, in your electrical wire, in your household and everything. Will you be able to track any single electron in those wires? Right? That's not possible. You guys cannot identify single electrons. No way. There's nothing you can do about it. All right. So that's the reason why what I'm saying over here is it's easier for you to think of potential energy per unit charge. Because if you want to calculate back what is the total energy, you just multiply by the amount of charge that you want to deal with. And this is the reason why when you use like a household value of the potential difference of 220 volt, this is your house potential difference. What you have is, okay, I just know that, I mean, I'm using 220 volts. And if I want to know like, hey, how many energy that I'm consuming by having the 1 coulomb charge running around this 220, you just multiply this thing back and then you get 220 joules. Does that make sense? Okay, so my conclusion is the whole point of the electric potential is just make it easier for you in the future. Right? All you need to do is just define the potential difference, and you can always use this to trace back the amount of potential energy that you need whenever you want. Cool.
Okay.
All right, so that's it. That's how simple it is for you to get connected between the potential energy and potential. I know the wording is annoying. You just drop the word energy, you get another quantity in physics, right? But that's the way it is, okay? So if you know that you have the different value in potential energy, okay, come back here again. So everyone now is supposed to agree with me now. This is high potential energy. And when you go along the field, that is low. So there will be no difference it's going to be the same thing as you call it the high potential. Same thing, right? And this is going to be low potential as well. Okay, so wherever it has a high potential energy, it's supposed to be the position that you have a high potential as well. It's just per unit charge. So the formula that you got from the previous page, what you need to do is I'm just moving that Q to the left-hand side. That's all I'm doing because I'm thinking of per unit charge. Or just like your friend suggested before, you can imagine that you take your charge to be 1 coulomb. Just make it disappear from your equation. That's all. So that's what it is. You get this equation instead. So the potential difference between 2 points is going to be potential at final point minus initial point. It's going to be exactly the same as the potential energy difference between those 2 points, but you calculate it per unit charge. So it's just like you get rid of that charge in that previous equation and you're down with this formula right here. Cool.
Okay.
And this gives you the connections between here. See that? You now know the connections between force, force and the field, energy and the potential. Field, potential, right there. They are all connected like this. And I can conclude to you guys that we only have these 4 things to calculate. It's either force or the field or either potential energy or just the potential. Okay. And once again, the unit of this potential is volts, is joule per coulomb. And that is done. Okay, guys?
Okay.
All right. And you're going to hear a lot of this word potential difference, right? It's much more easier to use and it's easier to talk about. You just call potential difference instead of talking about like potential energy difference. That's not very common to use. All right. But you can always use the potential difference and calculate back what should be the potential energy difference. We'll have some exercises for you to try, okay, how to calculate those. But before that, well, Ajahn, are you serious? Are you going to define the potential difference by having like the integral equation like this?
Okay.
It is, right? This is by definition, this is what it is. However, in reality, so we are pretty much like going to focus only into 2 cases, 2 big cases. One case, when you have constant electric field. Okay, when you have just a constant electric field, now everyone should be sort of agree with me now, John. This is easy now because we just already figured out that the potential energy difference is just negative QED, right? We already defined, calculated this. So if you just want just the potential difference between 2 points, you just drop that Q, you just take that negative E times D. So this is one case. That means you are given a field. You just be able to calculate the potential difference directly by taking the distance between 2 points in that field and you are done. Okay. So this is going to look exactly just like what you saw in gravitational fields. However, in the gravitational fields, we never define potential. No, we don't have gravitational potential. We always use potential energy in the gravity, right? That's all. We never use this concept of potential alone without the word energy. Okay, now come back to us. But the usefulness of this is when you have some more complicated scenario, that formula tells us something. Okay, guys, follow me here one more time. This one just to test your understanding. Okay, I have electric field now because electric field can point in any direction. So we're not gonna sort of confine ourselves with the downward, just like gravitational field anymore. So now let's consider what is going on. Just test your understanding here. If electric field pointing from left to right, guys. Okay, now I have 3 points for you to analyze. You have point A on the left, point B up here, point C down here. Okay, so find me the potential difference between A and B. If A and B are separated by that displacement vector S. Go ahead. One more time. We have electric field E pointing horizontally from left to right. You have 2 points A and B are connected through the displacement vector S. What is the potential difference from point A to point B? All right, I'm going to show you why that definition equation works so well. Look at this again. Whenever I want to find the potential difference from 2 points, all I need to do, just take that equation, take the field, dot with the ds. The reason we use dots because it came from the concept of work done from A to B. So far so good. Negative sign has to be there all the time. We understood that already. But because right now electric field is constant, D is also a constant in directions. So you guys still remember how to do the dot product. This dot product is just magnitude of E times the magnitude of the ds times the cosine of the angle between the two. Cool, guys? So far, so good. Now with that, electric field is constant. I can pull, okay, let me do it one more time, all right? You can forget about this one. It might confuse you a little bit. So let me do this. It's gonna be minus E integral ds cosine theta from point A to point B. Cool? But then what you can see about that, wait a second. When you do the ds cosine theta is this vector right here. Woo. So what I'm saying over here is, all you have to do is just, you don't have to do anything because the cosine theta is a constant. So you can also pull out cosine theta. You only have the integral of ds left from A to B. And let me do it one more time. So what you get is just here. Whatever you look at it, you look at it in terms of the vector, you look at it as just like completing the integral or whatever, but at the end, you get the s cosine theta term here. The s is the vector here, but when you do the cosine theta, you get the d vector right there. So at the end, what you get is negative E times D. Cool?
Okay.
If you guys agree with these results, does it surprise you in any way? The reason is no, Adan. That's no surprise because here, I have my mass here. I pull it up, it's MGH. But everyone knows, Adan, you can do in the diagonal direction if you want. Actually, as long as I sit on the top of my screen anywhere, they're sharing the same MGH. No different, Adan. All MGH. So it's gonna be same thing over here, but then you can tilt your head a little bit and think about this and like, okay, Adan, as long as you are at this level, they must be sharing the same potential energy. And because the potential is just potential energy per unit charge, you can talk about U or you can talk about V. They are pretty much the same thing. So that means at whatever point on this dash line here, it will share the same potential. Same thing down here. When you come down here, no matter where you are on this line, you're sharing another potential. And you also know this is high, this is low, because when you're going along the fields, you go in the direction that is lower your potential. Cool. So that's why I can go like this, and I can stop at some point here. You still get the same delta V from A to B. I can go, stop here. Doesn't matter. I can even go all the way out and come back here. It doesn't matter. It's just the same thing as, imagine the mass here. I can throw this mass to you and then you throw back and then stop at the top of the screen. The potential difference is still MGH. Cool? All right, so that's give you the conclusion that all we care about is just the location of the point that you are interested in. It doesn't care about the path. It doesn't matter you want to go from A to B, which direction, using what path, how you're going to go from it, from one to, I don't care. And that is a property of the one that we here. I didn't want to focus on this too much, but at least I just mentioned briefly about it because the electric force is a conservative force. Just like gravitational force is also a conservative force. Every time that you have this kind of property in it, the good thing about this one is whatever things that you do in work, it's going to be path independence, guys.
Okay.
Make your life a lot easier. Right? So you don't have to worry at all how you get from A to B. I don't care how. You start from here and you can just close your eye. Then when you open your eye, the mass is at the top of the screen. Everyone can tell me exactly what is going to be the change of the potential energy. You guys with me with that? All right, guys. So I hope that's half an hour of my talk. It's too much already. But I hope you get the whole idea of why we are trying to do this. All right. And why we have to refocus you guys with the origin of the potential and potential energy. Just want to confirm that you understand the definition of this, right? Even though you might have not done this back in the day of gravity, but now I think this is a good time to explain it in full detail here. All right, guys. But then I already said you have two sort of scenario that you have to deal with. This scenario is done when you already got the information about the electric field. Your life is pretty much easy to calculate the potential or potential energy because electric field is pretty much given. But on the other hand, the second scenario is this. What about you go back to the charge? We started everything with a charge. If you would like to calculate a potential around a charge, how would you do it? That's a question. You want to find the potential around the charge. Well, now that's going to be tough because in your formula, there's no Q on it. There's no charge around it. And that's where I want to skip. This is the part that I don't want to talk about. It will take too long. I used to do it. And I think it turns out we spent like half a lecture talking about this slide. And at the end, you guys still didn't really understand it. Because there's so many combinations into this. There is like you have the R hat problem again. Yeah, go. That's the R hat thing. You have to do the integral from one point to another point, and then now you have to deal with that crazy dot product along any curve path, blah blah blah. But oh, that's so crazy. But anyway, at the end, it's easier for you to grab the final result. The final result is this. See, if you want to go from point A to point B around a point charge, so let me highlight this one a little bit clearer here, that you have a point charge there, and you want to go from A to B, it turns out the potential difference, which means VB minus VA, can be calculated using this formula right here, KQ over R at B minus KQ over R at A. Because of this result, it have a tendency that you can say about John, we can grab this and call this a formula to calculate electric potential around any charged particle. And that's, we can get to this. That's it, done.
Okay.
Is that easier? I think it's just easier, just give you the result. Well, John, or this one, just forget about proving or forget about verification or anything. Let's take it, okay? So if you have a point charge, Q, and you are at some distance from that charge R, the potential value, potential, not potential difference, potential is going to be KQ over R. But then there is a problem here. We never actually use the pure potential because you always have that delta all the time, right? That's by definition, you must compare between point A and point B. To be able to use this formula, somehow you must have to compare this V to some point, right? There must be some location that you want to compare this potential from because it's always potential difference. And that's why you can take R at A to be infinity, guys. This is the weirdest one and it's annoying you guys the most. You always take your reference to be at infinity. And hence you take this term to be zero. And that's, you can name potential at point A to be just like go away. This is so far away, I don't care about it. So that's why this formula always imply that you take V to be zero at infinity all the time, just so you know, right? Because when you read the question in the problems on everything, there will be this sentence showing up. Take the potential to be zero at infinity all the time. That's just because we define the potential in this way. That's all. All right. But the good thing about this one is, see, it's KQ over R. You guys come back here a little bit. So now you are at some location away from point R. So that means as long as you stay at the same radius from that point charge, you are sharing the same potential. KQ over R. You guys with me? And if you want to move to a new R, that's when you're going to get another value of potential. Okay. So that means, so many means, if you want, sort of like, think of it like this one is exactly just like in a satellite orbiting around Earth. If you keep your orbit radius at the fixed value, you are still at the same potential level. And if you want to change your potential, you just have to jump to a different value. But then the way that you can jump, it just anywhere you like. As long as you start from initial R and you end it another R that are exactly the same, the potential difference are always the same. Okay, guys, I don't know would that complicated your calculations or whatever that's going on in your head at this point, but I would like to summarize into these two scenarios. Okay, so it's going to be easier for you to sort of like, arrange your thought a little bit. One is when you already given your electric field. So if this is the case, you can usually always be able to calculate the potential difference using the E times the D. Yeah, this is good. All right. However, there is another type of problem that you are given a charge or maybe like a bunch of charges lying around. Okay. And if that is the case, you just have to use V equal to KQ over R to help you calculate the potential from that point charge. And that's it. Those are the two things that you just have to know. Okay, it might sound confusing and then there are a lot to take at this point, but I hope by seeing a few of exercises, it will help. Okay, and we're just repeating this process a couple of times, it will be clearer. All right, right now, just so much. And because we have already seen the calculus in the electric field calculation problems, there will be no difference if you really want to calculate electric potential from a continuous charge distribution. So wait for it, guys. This is going to be a lot of fun. Okay. All right. But the whole thing is it. This is it. This is pretty much the content or the meat of the potential and potential energy material. It's just this. The rest, just give it a shot and see how can we calculate things here. All right. So let's do maybe a couple or a few exercises today, and then we can leave the rest for next time. So have your brain absorb or, sort of like, get things sort of like settle down in your head first, and then we can, look at more exercises next time. But this one will just give you a test of what is about to come here. The figure shows 4 arrangements of charged particles, all the same distance from the origin. Cool. Rank the situations according to the net electric potential at the origin. See that? One thing that you notice right away is now you have a distribution of point charges. So imagine in your head, you're probably going to use this KQ over R. Cool? All right. So this is one of the 2 scenarios that I told you about. This one, you don't get any value of the electric fields ready. There's no electric field given, but you are given the distribution of point charges. So you're supposed to use KQ over R somehow. All right, and they want you to rank the potential at origin. Which one is the biggest, which one is the smallest? And see, you look at the last sentence over here. Take the potential to be 0 at infinity. They already attached this line in every problem because that means it gives you permission to use this equation, because this equation implies that you take potential to be 0 at infinity. Cool. All right, guys, go for it. Let's calculate potential at the origin. So because this has a distance, let me call it A. Yeah, they gave you pretty much like same distance from the origin. So I can say the potential total is going to be K, start from the top, plus 2Q over A. Followed by the second one, K minus 9Q over A. And that is it, guys. Okay. Done. It seems like it's easier than electric field a lot. Okay. But the thing is that you have to be careful with is now electric potential or electric potential energy. These are scalar quantities. There's no more direction, only pure numbers. And you remember from the gravitational potential that you can have a negative potential when you dig a hole underneath your reference level, right? When you're above, that's a positive potential. When you are at the reference, that's your zero potential. And then you go below, you can have a negative one. So in calculation of the potential, you need to take the sign into account. There you go. That's why negative 9Q is there. And at the end, pull a common factor here, you get negative 2Q as your final of 7, sorry. Whew, 7Q there. That's done. Okay, let me call this case A. Cool?
Okay.
Not too bad. All right, try B. All right, so the total potential at the origin in the case B is going to be K. Start from the top one, negative 2Q over A plus, oh, no problem, K negative 3Q over A. So at the end, you get K over A, and then you get negative 5Q. Done. See, actually, it's a lot easier than electric field calculation. Because in the electric field, you have to do, vector summation, this one go there, this one, no. Let's just go ahead, all right? And then you just sum them all.
Okay.
All right, I think you get the feel of how to do the next one. But then they all at the same distance from the origin. So you're going to get like K, Q over A, K, Q over A, K. So K over A can be pulled out. It's a common factor. So now you start to see, Ojan, let me pull that K over A out. And all you need to do left is just sum all the charges, right? Does that make sense to you now? That's what you do. K over A is a common factor in all charges. Yeah. So over here, you just, okay, minus 2Q, minus 2Q, minus Q, minus 2Q. Just sum all the charges. So what you have in the case C over here is going to be minus 7Q. Nice. And now the last one will do the same thing. The total potential in the case D is going to be K over A. And then you do the sum of all these 4 charges. And now you have minus 7Q. And that's it, guys. You're done.
Okay.
So it turns out the most positive potential at the origin turns out to be case B right here. That's the highest. And then the rest, the other 3 cases sharing the same potential energy. And they are all negative. That's fine. Cool. Get the idea, right? Okay, one more time. All right. Here. All right. So we're going to take this one as our last example. Okay. But you can see that now you are given a distribution of point charges. So imagine in your head, you're probably going to end up using KQ over R relationship for sure. In the figure, 8 particles form a square with distance d between adjacent particles. What is the electric potential at point P, which is the center of the square? If, once again, you kind of, right. Potential is 0 at infinity. So you already give a ticket to use this formula right here, KQ over R. Guys, go ahead. Shall we? Let's start from the upper left corner. Here we go. Okay, so the distance from that to point P. Okay, what you are getting is going to be K, the charge that give you a potential is minus 4Q divided by, okay, this is going to be the diagonal directions here. It's going to be D root 2. You guys with me? Okay, because this is D. This is D. So the distance there is going to be D root 2. So it's going to be D root 2 here. Done. No need to square or anything. That's a formula for that. And now you move on to the next. Here we go. And now you do the distance there. Cool. Okay, so let's next go to the blue. What you have is going to be K minus 2Q over, now the distance over here is just D. Let's put it there, D. Nice. Now keep going to the next one. Now let me put the yellow again, plus Q, and then the distance is just there. But then, Majan, wait a second. It's the same distance as the first minus 4q on the upper left corner. Majan, yeah, that's exactly what it is. Plus k plus q over root 2d. Cool. Keep going, guys. Look at the next blue, minus 5q. The distance is here. So you say the next potential is going to be k, the charge minus 5q over the distance is only d. Now you start to notice something, I hope. If you move on to the next, the lower right corner, your distance from that is going to be the diagonal distance. So it's going to look like k plus 4q over root 2d. Move on to the next one. It's going to be the one on the side. The distance is going to be just d. So what you get is going to be k minus 2q over d. All right, last two, guys. The lower left corner. Oh. I think you kind of see where am I at when I put the color coded here. So all the greens are the charges from the corner. And they are placed at the same distance from point P. Of course, they are at the corner, which is a root 2D. So actually, if you already catch this one or you already observe or notice that, oh, Ajahn, we can actually sum all the charges at the corner and pull out the common factor of that k over root 2d. See, that will shortcut a lot of steps there. Cool. All right, but that's just this one just to give you like a straightforward way of calculation as well. So last step, guys, last one, plus 5q. The plus 5q is going to show up right there. So it's going to be plus, oops, that's still green. K plus 5q over d. So once again, if you notice, you can also categorize another team here. Next team is going to be the team on the side that's sharing the same common factor k over d. Okay, so at the end, all right, if you want to do straightforwardly, let's just what I just did, or you can just notice and then you can group them into two groups, the one at the corner, the one on the side. That will be fine. But at the end, this is what you get. You're going to get k over root 2d. And then just the sum of all this, and it's 0. See, the good thing is, if you notice that, oh, Ajahn, I can group all the charges at the corner, and then they have a common factor of k over root 2d. And then you just look at charge at the corner, oh, they sum to 0. See, you don't have to do anything. It's just gone. All those stuff at the corner is gone. And then you just say, okay, plus, now you have all the charges on the at the side. So what you have is you have a common factor of k over d. And then you look at the charge on the side, you just sum, oh, 5 and minus 5 just cancel. You left with just negative 4. And that's it, guys. You are done.
Okay.
That is your net electric potential at point P. It's just minus k 4kq over d. That's it. K4q. All right. You can rearrange whatever you feel fit. 4kq over d. All right. And you are done.
Okay.
Okay. Not too bad. All right. So I hope you learned something today. And then maybe I talked too much today, but that's what it is. All right. That's about the electric potential. And next time we're going to go deeper and more complicated problems, but at least you get the basic down today, guys. That's it for today. And I'll see you guys when next Monday. Yeah. Okay, guys. Take care. Bye-bye.